This section examines the principle of the clutch. A clutch connects and disconnects one rotating mechanical component from another. An automobile clutch transmits torque from the engine to the transmission, and the driver uses a release mechanism to control the flow of the torque between them. Most light vehicles use a single-plate friction-type disc, with two friction facings attached to a central hub, splined to accept the transmission input shaft. The friction facings are clamped between the flat surface of the engine flywheel and a spring-loaded pressure plate bolted to its outer edge. The input shaft passes through the center of the pressure plate to engage the splines of the friction disc hub. With engine rotation, the flywheel and clutch assembly rotate as one unit. Engine torque is transferred from the flywheel through the friction facings to the splined hub and into the transmission. Moving a clutch pedal operates the release mechanism to control the flow of torque between the two units. Depressing the pedal retracts the pressure plate against the force of its springs and frees the friction disc from its clamping action. Releasing the pedal reapplies the clamping force and reconnects the two units. This control is necessary when placing the transmission into gear. The transmission input shaft must be disconnected from the engine. When moving the vehicle from rest, slowly releasing the pedal gives a gradual engagement of the drive as the friction facings slip and allow torque to be applied progressively until both units are rigidly connected. When selecting an alternative ratio, that is, changing gears when the vehicle is in motion, the transmission of engine torque must again be interrupted for this to occur. And when bringing the vehicle to a halt, the transmission must be disengaged to leave the engine running at its idling speed. The amount of torque a clutch can transmit depends on the coefficient of friction between the friction facings and their mating surfaces, the mean radius of the facings, the number of facings in contact, and the total spring force. Increasing the diameter of a clutch increases its torque capacity, as does increasing the spring force. Two or more clutch plates can be used to form a multi-plate clutch, increasing the number of facings and torque capacity. They are useful where a reduction in diameter is advantageous or where increasing the spring strength is undesirable. Most light vehicles use a single-plate clutch to transmit torque from the engine to the transmission input shaft. The flywheel is the clutch driving member. The clutch unit is mounted on the flywheel's machined rear face, so that the unit rotates with the flywheel. The clutch unit consists of a friction-type disc with two friction facings and a central splined hub, a pressure plate assembly consisting of a pressed steel cover, a pressure plate with a machined flat face and a segmented diaphragm spring, and a release bearing and operating fork. The friction disc is sandwiched between the machined surfaces of the flywheel and the pressure plate when the pressure plate is bolted to the outer edge of the flywheel face. The clamping force on the friction facings is provided by the diaphragm spring. Unloaded, it is a dished shape. As the pressure plate cover tightens, it pivots on its fulcrum rings and flattens out to exert a force on the pressure plate and the facings. The transmission input shaft passes through the center of the pressure plate. Its parallel splines engage with the internal splines of the central hub on the friction disc. With engine rotation, torque can now be transmitted from the flywheel through the friction disc to the central hub. and to the transmission. When the clutch pedal is depressed, the movement is transferred through the operating mechanism to the operating fork and the release bearing. The release bearing moves forward and pushes the center of the diaphragm spring towards the flywheel. The diaphragm pivots on its fulcrum rings, causing the outer edge to move in the opposite direction and act on the pressure plate retraction clips. The pressure plate disengages and drive is no longer transmitted. Releasing the pedal allows the diaphragm to reapply its clamping force and engage the clutch, and drive is restored. This section examines operating mechanisms. Movement at the pedal pad is transferred through an operating mechanism to the clutch assembly on the rear of the flywheel. This mechanism may be mechanical or hydraulic. Mechanical systems may use a system of levers, but cable operation gives more flexibility and is more common. This is a cable-operated control for a front-wheel drive vehicle. The outer cable is fixed to the pedal box inside the vehicle and to the clutch housing in the engine compartment. The inner cable connects between the upper end of the clutch pedal and an external lever on top of the clutch housing. This lever is connected to a vertical shaft supported in the housing and attached internally to a release fork, which carries the release bearing. Depressing the pedal relays the movement through the cable, and the release bearing thrusts against the diaphragm fingers on the pressure plate. An adjustment on the cable provides for a minimum amount of free play to be maintained between the release bearing and the pressure plate fingers when the pedal is in the released position. This prevents constant contact of the bearing with the fingers and subsequent rotation of the bearing when the engine is running. A large force is required to depress the pressure plate fingers, so the system gives a mechanical advantage of around 8-to-1. This means the force applied at the pedal pad is magnified 8 times at the release bearing. The corresponding movement ratio can give a pedal movement of up to 200 millimeters, while the release bearing only moves a fraction of this amount. In hydraulic clutch control, the pedal acts on a master cylinder, connected by a hydraulic pipe and flexible hose to a slave cylinder, mounted on the clutch housing. The slave cylinder operates the clutch release fork. This vehicle uses a center valve master cylinder. With the pedal in the off position, the center valve is clear of the inlet port, and fluid can flow to or from the reservoir into the cylinder. When the pedal is initially depressed, the piston is moved forward, taking the valve assembly with it. The center valve closes off the inlet port from the reservoir, trapping fluid in the cylinder bore. Further piston movement displaces fluid through the outlet port and into the connecting lines to act on the slave cylinder piston. The movement of the slave cylinder piston is transferred through a push rod to the clutch release fork to operate the clutch. When the pedal is released, displaced fluid returns to the master cylinder, and the center valve returns to being slightly clear of the inlet port. In light vehicle applications, the pressure plate is normally a diaphragm type and is serviced as an assembly. It consists of a pressed steel cover, a pressure plate with a machined flat surface, a number of spring steel drive straps, and the diaphragm spring. This diaphragm is located inside the clutch cover on 2 fulcrum rings, held by a number of rivets passing through the diaphragm. The pressure plate is connected to the cover by the spring steel drive straps, riveted to the cover at one end and to projecting lugs on the plate at the other. Retraction clips hold the pressure plate in contact with the outer edge of the diaphragm. During clutch operation, they move the plate away from the flywheel. This section examines the driven center plate, also called a clutch disc or friction disc. The driven plate has a pair of friction facings, usually of wire-reinforced asbestos composition, carried on wavy spring steel segments, which are riveted to a steel disc. The central alloy steel splined hub is separate. Drive is transmitted from the disc to the hub through heavy torsional coil springs or rubber blocks. This spring hub arrangement dampens torsional vibrations from the engine. It also absorbs shock loads imposed on the driveline by sudden or violent clutch engagement. Stops limit the radial movement of the hub against the spring force. A molded friction washer between the hub and spring retaining plate also acts as a dampener. The waved spring steel segments cause the facings to spread slightly when the clutch is disengaged, then compress as it is engaged. This has a cushioning effect and provides smooth engagement. This section examines the throwout or release bearing. The clutch release bearing can be a thrust-type angular contact ball bearing supported on a carrier. It slides on a hub or sleeve extending from the front of the transmission. The bearing carrier locates on the clutch release fork. Moving the fork brings the bearing thrust face into contact with the pressure plate fingers. This causes the bearing to rotate and absorb the rotary motion of the fingers against the linear motion of the fork. The bearing is packed with lubricant during manufacture and requires no periodic maintenance during its service life. In light vehicle applications, the engine operates over a wide speed range, but produces maximum torque only within a relatively narrow RPM band. A relatively large turning effort must be applied to the driving road wheels to move the vehicle. Then the turning effort must vary to overcome air and gradient resistance and rolling resistance. A manual transmission allows the driver to directly vary the gear ratio between the engine and the driving road wheels. This allows engine torque to be varied to suit load and speed requirements. The transmission also provides a means of reversing the vehicle. And it has a neutral position, which disconnects the engine from the driving wheels. When 2 gears are in mesh, one is a driven or output gear. The other, providing the turning action, is the driver or input gear. A gear ratio is the number of turns of the input gear necessary to achieve 1 turn of the output gear. Here it is 1:1, since the gears have the same number of teeth. In rotation, they also turn at the same speed, and the turning effort of the output gear will equal the effort applied by the input gear, The gear ratio can also be calculated by dividing the number of teeth on the driven gear by the number of teeth on the driver gear. In this case, the driven gear has 30 teeth and the driver gear has 10. So the ratio is 3:1. The driver gear has to turn 3 times to turn the driven gear once. In continuous rotation, the driven gear turns 3 times slower than the driver. Lower speed produces higher torque. So torque at the output is higher. For this gear ratio of 3:1, if input torque is 100 Newton meters, then output torque is 3 times that, 300 Newton meters. When 3 gears are in mesh, the input and output gears are meshed with an idler or intermediate gear. The idler transfers movement between the input and output gears, but has no effect on the ratio or the torque multiplication. These remain unchanged. Compound gear trains have 2 or more pairs of gears in mesh so that they rotate together. This compound gear train has gears on 3 shafts. The gear on the input shaft meshes with a larger gear on a countershaft or cluster gear. The countershaft has a smaller gear formed on it, in mesh with the output shaft gear. The motion of the input is transferred through the large gear, along the countershaft to the smaller gear, to the output. The output turns in the same direction as the input, but at a reduced ratio, depending on the relative sizes of the gears. Since 2 pairs of gears are involved, their ratios are compounded or multiplied together. The input gear with 12 teeth drives its mating gear on the countershaft, which has 24 teeth. This is a ratio of 2:1. This ratio of driven over driver at the input, 2:1, is then multiplied by the output ratio, which has a driven to driver ratio of 3:1. This gives a gear ratio of 6:1 between the input and the output, resulting in a speed reduction and a corresponding increase in torque. Gear reductions in the lower gears of manual transmissions can be provided by compound gear trains. Typical ratios are first gear 4.41:1, second gear 2.63:1, and third gear 1.61:1. Fourth gear is normally a ratio of 1:1. The input and output shafts turn at the same speed. There is no torque multiplication. A fifth gear is normally an overdrive ratio, typically with a value of 0.87:1. Then the output shaft turns faster than the input, but the output torque is reduced. A further reduction is always provided by the final drive gears. Their ratio is included when calculating overall gear reduction. The overall gear ratio is the gearbox ratio multiplied by the final drive ratio. A gearbox ratio of 3:1 with a final drive ratio of 4:1 gives an overall ratio of 12:1. 12 revolutions of the crankshaft result in 1 turn of the driving road wheels. Assuming 100% efficiency, the torque applied is 12 times the engine torque, although this is divided equally between the driving wheels. This section examines gearbox layouts. In a manual transmission for a rear-wheel drive vehicle, the gear train is built up on 3 shafts. The input shaft extends from the front of the transmission. An external parallel spline section engages with internal splines on the clutch-driven plate. A main drive gear is an integral part of the shaft. It meshes constantly with a mating gear on a countershaft, which has a number of gears formed on it. These gears mesh with mating gears on the main shaft or output. These main shaft gears are supported on bearings on the shaft. They can rotate without turning the output. Each main shaft gear has an external toothed section on one side. The teeth face an internally toothed engagement sleeve located on a central hub, which is itself splined to the main shaft. The engagement sleeve can slide in either direction to engage the external teeth on the appropriate gear. This locks the gear through the sleeve and hub to the main shaft. Before engagement of the components occurs, a synchromesh device between the sleeve and gear synchronizes them. The gears constantly in mesh have their teeth cut on a helix at an angle to the gear center line. This reduces gear noise and distributes load more evenly, as several teeth are in contact at any one time. Teeth on the reverse idler are normally straight cut or spur gears, cut parallel to the gear center line. When reverse is selected, this connects the reverse idler with mating gears on the countershaft and main shaft. The reverse idler rotates on a plain shaft fixed in the casing. It transfers the drive from one shaft to the other and reverses the direction of rotation of the main shaft. In transaxle designs, the drive is transferred through the clutch unit to a primary shaft. In this example, the primary shaft carries gears of different sizes, meshed with gears on the secondary shaft. Each pair has one gear fixed to the primary shaft and one free to rotate on bearings on the secondary shaft. An engagement sleeve and hub with a synchromesh unit facing each gear is on the secondary shaft between first and second, and similarly between third and fourth. The engagement sleeve moves to engage the dog teeth of the relevant gear when a gear is selected. This locks the gear to the shaft so drive can be transmitted. A drive pinion gear fixed to the end of the secondary shaft is constantly in mesh with a final drive ring gear. The drive is transferred through these gears to the differential unit. A reverse idler transmits the drive from the primary to the secondary shaft when reverse is selected. A 5-speed transmission has an extra fixed gear on the primary shaft, meshed with a mating free gear on the secondary shaft. The free gear has its own engagement sleeve and synchromesh unit beside it. Selecting 5th gear locks the gear to the shaft. The gear on the primary shaft is larger than the gear on the secondary, so an overdrive ratio is provided. The secondary shaft rotates faster than the primary. Gears constantly in mesh use helical gearing. Having the gearbox and final drive gears in one casing provides a compact and noise-free unit. This section examines gearbox operation. In a rear-wheel drive manual transmission, the splines on the input shaft engage with the splines of the clutch-driven plate. With engine rotation and the clutch engaged, the input shaft transfers its motion through the countershaft to rotate the gears on the main shaft. In this neutral condition, the engagement sleeves and hubs splined to the output shaft are stationary. No drive is transmitted to the output. Depressing the clutch pedal removes the engine load from the input. This allows an engagement sleeve to be moved into engagement with the external teeth on the gear selected. This locks the gear to the main shaft. When the clutch is released, the drive is transmitted to the input gears along the countershaft to the gear selected. Since this gear is now locked to the main shaft rotates and transfers the drive to the final drive unit. The speed ratio and the torque transferred depend on which gear is selected. In this 4-speed transmission, first gear, the smallest on the countershaft, meshes with the largest gear on the main shaft to give first gear. This is the lowest forward ratio. The greatest number of turns of the input are required to achieve 1 turn of the output. This also gives the greatest torque multiplication. In second gear, power flow is through the next adjacent gear. The difference in speed between input and output shafts is reduced. Fewer turns of the input are required to give 1 turn of the output, but there is less torque multiplication. When the engagement sleeve for third gear moves into place, drive is transmitted through the meshing gears at an even higher ratio. In fourth gear, the input and output shafts are locked together. This provides a direct drive with a 1-to-1 ratio, with no reduction through the countershaft gears. The input and output shafts turn at the same speed, and therefore there is no torque multiplication. The countershaft gears and their corresponding gears on the main shaft continue to rotate, as the countershaft is constantly in mesh with the input gear, but they do not transmit any drive. With the vehicle in motion, these gears will be turning at different speeds in relation to the main shaft and to the engagement sleeve, which is locked to the main shaft by the spline. When changing gear, their speeds must be synchronized so that the engagement sleeve can move smoothly into engagement. A Bork ring type of synchromesh unit is commonly used to synchronize the speeds of 2 gears before engagement. 3 metal inserts with a ridge fit into slots in the hub. A radial spring at each end holds them out, so that the ridges locate in a groove inside the sleeve and hold it centrally on the hub. When the synchronizer is assembled, the hub is splined to the main shaft, and the engagement sleeve is splined to the hub. A bronze Bork ring with recesses to accommodate the ends of the inserts is located in each end of the hub, and a conical inner surface faces a matching steel cone on the gear. fine grooves are machined on the conical surface, and the teeth on the outer edge are the same size as the dog teeth on the gear and the spline on the sleeve. The recesses are wider than the inserts to allow the balk ring to move radially. Then the teeth on the balk ring can be out of register with the teeth on the sleeve. When the sleeve is moved to select a gear, the spring-loaded inserts move the balk ring into contact with the conical face of the gear. The grooves in the face of the balk ring help to break through the oil film, and the difference in speed of the two components causes the balk ring to be dragged around with the gear to the limit of the recesses, where it is held by the inserts. Since the teeth of the balk ring are now out of alignment with the teeth of the sleeve, this balks or prevents the sleeve from moving over the ring into engagement. The force exerted by the driver now presses the sleeve against the teeth of the balk ring and forces the conical face against the cone of the selected gear, until the friction created causes the two components to rotate at the same speed. The balk ring teeth can now come into alignment and the sleeve slides over them and into engagement. This is assisted by a chamfer on the teeth, which helps to guide the sleeve into position. Smooth and rapid gear changes are thus ensured. In transaxles, the synchromesh unit plays a similar role. It is located between the end of each engagement sleeve and the gear. In this layout, the engagement hub and sleeve for first and second gears is on the secondary shaft, as is the third and fourth speed hub. The fifth gear engagement hub is at the end of the secondary shaft, furthest from the main drive pinion. When first gear is selected, the engagement sleeve locks the first gear to the secondary shaft. When the clutch is released, the drive is transferred through the fixed first gear on the primary shaft to the locked gear on the secondary shaft. The secondary shaft rotation transfers the drive through the main drive pinion to the final drive ring gear and the differential case. In first gear, the smallest gear on the primary shaft drives the largest gear on the secondary shaft, and this gives the lowest ratio, in this case 3.4 to 1. In second gear, a higher ratio is obtained as the fixed second gear on the primary shaft is larger. Fewer turns of the primary shaft are required to obtain one turn of the secondary. In this case, 1.95 to 1. In third gear, the engagement sleeve locks the freely rotating third gear to the secondary shaft. Drive is transferred from the fixed gear on the primary shaft to the locked gear on the secondary, and then to the final drive. The drive transfer is similar for fourth gear. The fifth gear ratio is provided by transferring the drive through the fixed fifth gear on the primary shaft to the engaged fifth gear on the secondary shaft. This is often an overdrive ratio, with the driving gear larger than the driven gear, making the driven gear rotate at a higher speed. For reverse, the reverse idler moves to mesh with a reverse gear on the primary shaft and the matching gear teeth on the outside of the first and second gear engagement sleeve. Drive transfers through the idler to the spline secondary shaft sleeve. The idler between the shafts makes the secondary shaft rotate in the reverse direction. This reverses the direction of the final drive ring gear and the road wheels. This section examines gear selection. A gear shift lever allows the driver to manually select gears via a gear shift mechanism. The lever can be mounted remote from the gearbox, on the floor or on the steering column, and connected to the gearbox by a rod linkage or cables. It can also be mounted in the top of the gearbox, where it acts through a ball pivot in the top of the extension housing. In this design, the lower end of the gear lever fits into a socket in a control shaft inside the transmission extension housing. A short lever on the other end of the shaft is located in a selector gate, formed by slots in the 3 selector shift rails. They are supported in the casing and are moved backwards or forwards by the lever. One rail moves to engage first or second gear, another serves to engage third or fourth, and the other operates fifth or reverse. A selector fork is attached to the first and second shift rail. It sits in a square section groove on the outside of the first and second engagement sleeve. Similarly, for the selection of third and fourth gears, the reverse selector fork engages in a groove in the reverse engagement sleeve. Lateral movement of the gear lever positions the control rod in line with the appropriate selector rail. Longitudinal movement is transferred through the control rod and selector rail to the fork and the engagement sleeve. Each rail has a detent mechanism, usually in the form of a spring-loaded steel ball held in the casing. The ball engages in a groove in the rail when the gear lever is in neutral, and in a similar groove when a gear is selected. This holds the gear in detention in the selected position. When a gear is changed or selected, an interlock mechanism prevents more than one gear being engaged at the same time. In this design, 2 steel balls locate in the casing between the center and the outside shift rails, and in alignment with grooves machined in the shift rails. A small plunger is captive in a hole drilled in the center rail. In the neutral position, the balls and plunger can move laterally. But when an outside rail is moved, the ball is pushed sideways to contact the plunger and move the opposite ball into the groove of the other outside rail. The 2 balls held in the casing prevent movement of the interlocked rails and hold them in the neutral position. When the center rail is moved, the balls move into the grooves of the outside rails and hold them in a similar manner. All gearboxes are fitted with interlock and detent mechanisms, although designs vary according to manufacture. This section examines bearings, seals, and gaskets. In a manual transmission, the gears and shafts are supported on bearings or bearing surfaces. This allows for rotation and also maintains the alignment of the components. The type of bearing used at each locating point depends on the load which must be sustained. Radial loads try to force the gears and shafts apart. The bearing, therefore, carries the load along its radius. Thrust loads are applied along the length of the components, so the bearing must cater for side thrusts. In many cases, these loads are combined, and some bearings designed for radial loads will also accept light thrust loads. This applies to most ball bearings. Single-row, deep groove ball bearings normally support the input shaft and main shaft in conventional rear-wheel drives. They can also be used at each end of the countershaft. The helical gearing creates radial and thrust loads as the gears try to force each other apart and move endwise. A circlip in a groove on the outside of the bearing can locate each shaft in the casing and maintain the alignment of the gears and engagement hubs. Roller bearings are common where loads are purely radial. Needle roller bearings can be caged or as a loose number, assembled to operate directly on a hardened gear or shaft. Typical applications are the spigot on the front of the main shaft, supported in the rear of the input shaft, and in some cases on the counter shaft, and the freely rotating gears on the main shaft. Separate thrust washers can retain them and cater for thrust loads. They are often a selective thickness to allow for end float adjustment. Thrust washers are plain bearings. They are usually bronze, but can be steel, with the bronze facing on one side. They can be dimpled or grooved to allow for lubrication. A plain bearing can also be used in the extension housing to support the front of the propeller shaft. Machined and hardened surfaces on the main shaft can provide bearings for the freely rotating gears. Flanges and snap rings on the main shaft locate the gears and cater for end thrust. A plain bearing is also used for the reverse idler. Taper roller bearings are normally used in pairs and can sustain heavy radial and thrust loads in either direction. They are commonly used in transaxles, where they support the front and rear of the primary and secondary shafts and the final drive assembly. Shims or selective washers can be used to provide for adjustment of preload. The bearings can be lubricated by being submerged in gear oil or by oil splashed about inside the casing. Where the shafts extend from the casing, oil seals prevent oil leakage and the ingress of dirt and moisture. Garter spring lip type seals are normally used. They can be single or double lipped, depending on the application. They can also be hydrodynamic type seals, with helical flutes molded into the sealing lip. The flutes create a pumping action as the shaft rotates, so any oil at the sealing edge is drawn back inside the casing. Since the flutes are molded in one direction during manufacture, care must be taken to ensure they are correctly applied, considering the direction of shaft rotation. O-ring type seals are mostly used for static locations, such as the speedometer drive gear housing, while gaskets are used to seal the mating surfaces between the casing and retaining plates or housings. In some cases, the gaskets may be used as selective thickness shims or spacers in addition to their sealing function.